In this video, I'm going to talk about special theory of relativity as the theory of matrices. So as we all know, things go crazy when an object have a velocity which is comparable to the speed of light, or it is experiencing some acceleration or gravity. So when an object has a velocity which is much smaller than speed of light and there is no acceleration, then we can use Galilean matrix to change from the reference frame to the moving frame. And if the velocity is comparable to the speed of light but there is no acceleration, then we can use Lorentz matrix, which was developed by Lorentz and then was used in special theory of relativity by Albert Einstein. When we have velocity comparable to the speed of light and the acceleration is non-zero, then we have to use Jacobian matrix, which was developed by Rindler. And in a case when an object has a velocity comparable to the speed of light and the acceleration is also non-zero and we also have gravity, then we have to use Riemannian matrix tensor, which was used by Albert Einstein to develop the general theory of relativity. First, I'm going to talk about Galilean theory of relativity. So Galilean theory of relativity is applicable when we have speed of an object much less than speed of light and there is no acceleration. So we have like a rest frame and then we have a moving frame, and we can change from moving frame to the rest frame by using inverse Galilean matrix like this. So this is a vector in the moving frame of reference and this is a vector in the rest frame. Once we have this position vector, we can also calculate the velocity vectors and also the acceleration vectors. One of the most important things to understand in relativity is covariant and contravariant vectors and covariant and contravariant components. For example, if you have a vector r which has a component a along the basis vector t hat and you have component b along the basis vector x hat, then the basis vectors t hat and x hat will change from rest frame to the moving frame using the normal matrix, and the vectors those use the normal matrix to change from rest frame to moving frame are covariant vectors. Similarly, the components of the vector they change from rest frame to the moving frame using the inverse matrix, and the vectors those use the inverse matrix to change from the rest frame to moving frame are contravariant vectors. In Galilean theory of relativity, the x hat basis vector they remain unchanged. Meanwhile, the t hat basis vector they change to produce the effect of Galilean relativity. Now let's see why exactly the special theory of relativity was developed. So there were some anomalies in the electromagnetic interaction. The electromagnetic interaction of the moving bodies, the magnet or the conductor, were not reciprocal. The outcomes are motion dependent, whether the magnet or the conductor is in motion. So in the first case, when the magnet is moving and conductor is fixed, the moving magnet produces an electric field in the vicinity which produces an electric current in the rest conductor. Meanwhile, in the second case, when the conductor is moving and the magnet is fixed, then the conductor experiences a changing flux which induces EMF in the conductor, which in turn produces a current in the conductor. After discovering these anomalies, Einstein said this:
"It's not Maxwell who gets it between the eyes, it's Newton."
What are you saying?
Time is not absolute.
Holy hell.
Now let's talk about special theory of relativity more in detail. As the postulates of special theory of relativity, Einstein said, all the laws of physics, including those of mechanics and now also the electromagnetism, are invariant in all the inertial frames, and the speed of light is constant irrespective of speed of object emitting it. That means the speed of light is constant in all the inertial frames, and now the speed of light is also a law of physics. Special theory of relativity is a case when the speed of an object is close to speed of light and the object doesn't have any acceleration. And the 4 vector from the rest frame can be transformed to the moving frame using the Lorentz matrix, where gamma is 1 over under root 1 minus v square upon c square and beta is equal to v over c. Now let's understand this more in detail by using the same example of a vector that we used in Galilean theory of relativity, which has a basis vector t hat and the x hat and the components a and b. The basis vectors, they transform from the reference frame to the moving frame like covariant vectors, and they use normal Lorentz matrix. Meanwhile, the components, they change like contravariant vectors, and they use inverse Lorentz matrix for the transformation. So in the special theory of relativity, the x prime basis vector and ct prime basis vector, they both change their direction. Meanwhile, in the Galilean theory of relativity, we saw that the x prime doesn't change its direction. T prime basis vector changes its direction from vertical to tilted. Now let's understand the Minkowski diagrams, Lorentz metric and Minkowski metric. So Lorentz metric is something that remains unchanged after the Lorentz transformation. So this vector R is a 4 vector, and the dot product of a 4 vector remains unchanged after the Lorentz transformation. We can write the Minkowski metric or the Lorentz metric in the matrix form like this. For instance, if we have a space which is defined by the basis vector x hat and ct hat, then after the Lorentz transformation, the x hat will change to x prime hat and ct hat will change to ct prime hat. And the yellow line defines the direction of light, which also forms the light cones. So we all know that the special theory of relativity breaks when there is an acceleration in a frame. So in this case, we have to use Rindler's transformations. This is a case when the speed of an object is close to the speed of light and there is acceleration in the frame. The first thing is that the special theory of relativity works perfectly fine with the acceleration, but it actually fails to describe the gravitation. The Lorentz transformation, they change from inertial to inertial frames, but the Rindler's transformation, they change from inertial to non-inertial frames. So in this case as well, we can use analogy of a vector which has a component A in t hat direction and b hat in x hat direction. The basis vector, they change from rest frame to moving frame using the normal Jacobian matrix like covariant vectors, but in this case, the matrix elements are actually dependent on basis vectors. We can easily calculate x prime and ct prime using this transformation rule. Just like the Galilean relativity and special theory of relativity, the components change like contravariant vectors and they use inverse Jacobian matrix. After the transformation, the Rindler space looks like this, and we can see the basis vector, they change at each point of the trajectory. So this is one of the main conclusion of this video, which is the relativity is just a Jacobian transformation. This is the Jacobian matrix we used for Rindler's transformation. We can see as a proof that if we apply Jacobian on the Galilean transformation, then we get Galilean matrix. Similarly, we can also apply Jacobian on Lorentz transformation to get the Lorentz matrix. Till now, all of the relativistic cases that I explained, they can handle the objects moving close to the speed of light or the objects with the acceleration, but they completely fail in case of gravity. For that, we need general theory of relativity, which includes all the effects of gravity. The general theory of relativity assumes that local gravitation is same as acceleration, which is also known as equivalence principle. Following are the topics required to understand the general theory of relativity, which I will cover in the next video. In the general theory of relativity, I'm going to cover the general metric tensor, the Riemann curvature tensor, then how to reduce the Riemann curvature tensor to Ricci curvature tensor, and then to Ricci scalar. I will also cover the energy momentum tensor, the cosmological constant, and the field equations.